sinusoidal output, which is what you are really aiming at. So that is why you need artificial nonlinearity to be put in additionally.
Okay, sir. Thank you.
Okay, anything else? Okay, I did not put up any new videos this week for the simple reason that I realized that there's only one more week. No time at all for you to learn entirely new things. So instead of putting in too much pressure on you with adding a lot of topics, there are two major topics which we have not covered. One of them was not in the syllabus but should have been. That is the subject of regulators, regulated power supplies. And the other is basically digital circuits of a special kind, things called counters, registers, and so on. Now, usually earlier this course, this theory course was not there, at least was there in the second year only, was not in the shorter course. We did not have a third year course, theory course in electronics. So then the theory part was always handled along with the lab course. So I've already talked to the instructors of next semester's lab course. The small pieces that I have not covered. One is regulated power supply, which is not really in the syllabus. That was always covered during the discussions in the lab. And the other is this digital registers, counters, and so on. They will be covered in the next sem, partly in theory in the online part, and a bit of that will be covered hands-on later on. So I'm not going to try to push in too much of that stuff in the last week. Today, I'm just going to describe some small bits of digital circuits, at least things which you have to know to round off this part of the course. So to begin with, let me just talk about one very simple thing. That is, how do you actually make an OR gate or an AND gate or an NOT gate? Now, firstly, a word of warning. This is not how OR, AND, or NOT gates are actually made, the ones which you really get to buy in integrated chips. These are the basic ideas behind those components. However, the actual circuits have some more amount of circuitry in there, which sort of limit the input current, protect the output from shorting, and other kinds of fail-safe devices are built in. But for the timing, let's just try to understand this. This is pretty straightforward. This is how you make an OR gate. And this is something you're going to construct in the lab next time around. This is how you construct an OR gate using two diodes and a resistance. Two diodes because you are talking about two input OR gate. If you had more inputs, you would have to add more diodes. The basic idea here is very, very simple. If A and B are both low, remember, of course, that when you say you're giving a voltage to the point A, you can never give a voltage to a single point. When you say you're giving a voltage to a point A, you're actually giving a voltage between this point and the ground, which is down here. And when you're taking the output here, which I've marked F, the output is between this point again and the ground. So it's basically the voltage across this resistance R. So if both A and B are 0 volts, then there is no voltage anywhere in the circuit. No current will flow because the diodes are unbiased completely. And as a result, what will happen is there is no voltage drop at all across this resistance simply because there's no current. So the output will be 0 volts. That's straightforward. If instead you made A0, say 5 volts. Oops.
Excuse me, sir.
Yes.
You're not present.
Oh,
Yeah,
I'm not.
You are not presenting, sir.
Sorry. Yeah. So that's one of the stupidest things one can do, but okay. So now that I've started the presentation, let's go back. This is a circuit which you should have seen a long time ago. It is two diodes and a resistance. Just that. And as I said, these points are marked and we are going to give some voltages to these points. And when I say I'm giving a voltage to a point, I really mean a voltage between that point and the ground. So we started by saying if both inputs A and B are 0 volts, then of course there's no voltage in the circuit at all. This end is anywhere at 0 volts. So there will be no current in the circuit because the diodes are unbiased. And because the diodes are unbiased, no current will flow anywhere, no voltage to cause the current to flow. And so there's going to be no drop across the resistance, and F, the output, is actually measured between this point and the ground, which means there's a voltage across the resistance. So in this case, 2 0-volt inputs. So let's say A and B in volts, I'm measuring that, and I'm measuring F as well. If I did this in an experiment, I will get 2 zeros, give you a 0. That's sort of easy. What happens if I, instead of giving 0 volts here, I had 5 volts here? So A is 5 volts and B is still 0. Now what will happen? Now diode D1 will get forward bias, D2 is still reverse bias. So the current will flow like this, will not flow through D2, the entire current will flow through R. So now there's a current through R, so there will be a voltage drop across R. How much voltage drop? That's also pretty easy to figure out. It's just 5 volts minus whatever the drop across D1 is. And the drop across D1, which is forward bias, is typically 0.6 to 0.7 volts. So if you assume it's 0.7 volts, then this is going to be 4.3 volts. Similarly, if you had 0 volts here and 5 volts in B, then D2 would be forward biased, current would flow through R, D1 will be reverse biased, so no current will flow through D1 in that case. But once again, the voltage across R is going to be 5 volts minus the drop across D2. So a bit less than 5 volts. But remember, 5 volts or 3 volts is what you would typically call high or 1. And if both were 5 volts, then both diodes will be forward biased. Okay. So what will the voltage here be? Can anybody tell me that? If both diodes are forward biased, what will be the voltage across the resistance R? Somebody unmute and tell me what the output will be. Of course, because I'm calling it an OR gate, it's obvious that 1 0 should give you 1, 0 1 should give you 1, which we have already achieved, and 1 1 should give you 1. But when I say 1, how much is it?
4.3.
Okay, it looks like it's going to be 4.3 volts. However, that of course is correct only if you assume that a forward bias diode always drops 0.7 volts. Strictly speaking, that's not true, right? Strictly speaking, when you forward bias a diode, the drop is something like this. There's a variation. It's not fixed at 0.7 volts. There's a slight variation. So can anybody tell me this? That if I made both ends 5 volts, will this drop across the diodes be more or less than the drops previously? In other words, will this be 4.3 or will this be slightly more or less? Say with both diodes forward biased, do you expect the same amount of current to flow through D1 now as it was when A was only 5 volts and B was 0? Will the current through D1 be the same now?
So if both diodes are forward biased, then the current through both diodes will actually be half of the previous value.
Well, almost half. Half assuming the same drop.
Yes.
But it's really almost half. But yeah, it is going to be less, definitely. Because now you have two paths which will allow current to flow. And these two currents add together to form the current through R, right? So if the drop across R were exactly the same as before, then of course the current would have been halved. But even if it's not halved, it's close to halved. The smaller current actually means smaller drop, right? Okay, I admit that smaller is smaller by a very small amount. There's not a resistance, so smaller current does not mean smaller drop in that proportion. But a slightly smaller drop, which means this voltage could typically be something like 4.4 or 4.5 volts. But frankly, those details don't really matter as far as digital circuits are concerned, because if you translate these to lows or highs or ones and zeros, this becomes 0, 0 gives a 0, 1, 0 gives a 1, 0, 1 gives a 1, 1, 1 gives a 1, and that's it. So it's this really, this whether it's 4.3 or 4.4 doesn't really matter, both count as 1. So what you have got here is a circuit which implements the OR gate. Now, of course, if you actually strung together a lot of such OR gates one after the other, the trouble would be, since the voltage is dropping every time, soon it might so happen that what you started out as 1 and should have been 1 ends up looking like a 0 because it has dropped too far down. Which is why you don't really use this circuit in a commercial situation. You add some more things to it to ensure that the voltage will not drop down that much and so on. But this is basically the idea. Okay, how do you make the AND gate? Well, the AND gate is similar, except that the two diodes, if you compare the OR and the AND, okay, they're hard to see them both together. But okay, one thing, the diodes have been reversed. Okay, they're now pointing towards the input, the arrows at least. And the resistance, instead of being connected between the output point and the ground, is actually connected between output and plus 5 volts. And every voltage, of course, is measured with respect to some ground, which is not directly connected to any of these components, but will be connected via whatever source you connect. So here, what happens is, if either A or B or both are 0, okay, if any one of A or B is 0, then at least one of the two diodes become forward biased, right? You have 5 volts at this end. If this end is at 0, if both ends are at 5 volts, then there is no bias in the circuit. But if one end is at 5 volts, the other end is at 0, then there is a forward bias in the diode. And the diode, say, if A is 0 and this is, say, 5 volts, then this diode D1 is forward biased. So current flows through this. And as a result, what's happening is, because current is flowing, the voltage across, there is a voltage drop across R, which means the voltage at this end comes down. Now, this is something which may take a bit of thought. The current here actually makes voltage come down, but you have already seen that before. Large amount of collector current in a transistor circuit would make the collector voltage go down. Here, what's going to happen is, larger the current, the smaller this voltage. But ultimately, how much voltage will be measured here? That's easy, because between this point and the ground is the same thing as between this point and A, right? Because A is grounded. And what is there between this point and A? There is a diode which is forward biased. So a forward biased diode drops around 0.6 volts. So F will be around 0.6 volts. So if either A is 0 volts or B is 0 volts or both are 0 volts, what happens is at least D1 or D2 or both will be forward biased. And because D1, D2 or both are forward biased, the current will flow through this resistance and there will be a voltage drop across this resistance. And the other end of the resistance, where you're measuring the output, will be at a low voltage. How low? If we had been using ideal diodes, then this would have been at 0 volts. But because we are using non-ideal diodes, it's actually at 0.6 volts or so, or 0.7 volts. That depends on your component, the circuit, or on your ingredient which makes up the diode. Now, if both are at 5 volts, then there is no bias in the circuit. Because there's no bias in the circuit, there's no potential difference, right? That's what makes current flow. And because there's no potential difference in the circuit, there will be no current. And because there's no current here, there's no drop across the R, so F will measure at 5 volts. So here, you're going to get 5 volts output only if both inputs are at 5 volts. If any one of the inputs is 0, the other, the diode is going to go forward biased, and F is going to read as at around 0.6 volts, which is low. So this is the AND gate, right? It gives you high only when both inputs are high, otherwise it gives you low. So far so good? Any questions? Okay, so we have handled the OR and the AND. The NOT gate is one gate which you cannot construct using diodes and resistances. What you need for a NOT gate is a transistor. In fact, what you need is really a CE amplifier of the kind that we have already done, but a much simpler version. You have just a bias resistance RB here between A, the input. There's of course a single input, and the base of the transistor. The emitter is shorted to the ground. And the collector is connected to the VCC, which is plus 5 volts in most digital applications. And the output is taken from the collector terminal. Now notice this condition here. If you remember your transistor biasing, this is exactly opposite to the condition you would want to keep the transistor in active region. In other words, notice that when both are plus 5 volts, say if A is high, then A is plus 5 volts. This is also at plus 5 volts. So both this end and this end start at the same voltage now. In that case, the current, there will be a current through the base, there will be a current through the collector. The current through the collector, of course, will be beta times larger. What you want to ensure is, despite having a much larger current, well, if you wanted the transistors to stay active, you would want the collector to stay above the base in potential, which would mean that despite a much larger current, a current which is beta times larger, the drop across RC should be less. That is, if you wanted the transistor to stay in the active region. Here, there, the condition that you would end up with is actually exactly the opposite of this condition. You would want RC to be less than RB by beta. This is for active. Smaller drop across RC despite having beta times more current, so that the collector ends up above the base. Here, we are doing exactly the opposite. We are demanding RC is bigger than RB by beta. Not only that, we are actually demanding that it be quite a bit bigger than RB by beta, typically say 10 times bigger at least. And you should realize that that's a pretty easy thing to achieve, right? Because beta being somewhere of the order of hundreds or 200s, all you have to do is just use equal RC and RB. Just put 1 kilo ohms in both. This condition is definitely satisfied. It's much easier to saturate a transistor than to keep it in the active region. Just use equal resistances. It's going to go into saturation if A is plus 5 volts. Why do we want much bigger? Because you might argue that if it's just bigger, that's enough for saturation. Why do you want it to be much bigger? Simply because you want to drive it into something called hard saturation. In other words, you don't want to take a risk that because of some small variation in temperature or some other operating point, beta itself has changed and therefore the transistor is no longer saturated. What you want to ensure is the circuit will go into saturation, and no amount of small changes in circuit's components will change that. Okay. So it's not only driven to saturation, it's driven to what is called hard saturation. You want to ensure that it's going to be saturated, but that means this voltage here between collector and emitter is actually smaller than the voltage between base emitter. So VCE would be actually typically smaller than 0.7 volts. But anyway, all this really means is A is high, A is plus 5 volts. The base emitter junction is forward biased, current flows here. As a result, current flows here. The drop here is so big that this transistor is driven into saturation. The output is going to be small. Whether it's 0.7 or how much less it is from 0.7, I don't really care. Because all we really need to worry about is the transistor now is in saturation and you've got a low output. High input, low output. Well, if you change this to 0 output, 0 volts, what will happen? Then the base emitter junction is unbiased, so it's cut off. As a result, very little current will flow through RC. There will be a tiny current because of minority carrier current, the ICEO, but that's tiny. So what will happen is there is no drop across RC, and no drop across RC means output will be the same as what is the voltage at the other end of RC, which is 5 volts. So if A is 0 volts, the transistor will be cut off and the output will be 5 volts. So 5 volt input, 0.7 volts or less output, 0 volt input, 5 volt output. That's exactly what you need for a NOT gate. Okay. So this is how you make a NOT gate using transistors. And these are circuits which you are actually going to make in your lab. And these are very simple circuits. Of course, these are, once again, these are not the actual circuits used in a professional level chip digital gates. However, these are the hearts of those circuits. Okay. Now that we know this, okay, are there any questions about this? or can we move on to the next topic? Seems to be no questions. Okay. So the next topic that we talk about is something which partly you already know. We will discuss some important combinatorial Boolean circuits. Combinatorial here has two important connotations here. One is combinatorial because what you do is you combine Boolean gates together, all these digital gates, and or not, or NAND NOR. We just combine them together and form circuits. However, there's a specific meaning to the word combinatorial here. The specific meaning is that this circuit is memoryless. These circuits that we are going to talk about are memoryless. That is, they don't depend upon what happened earlier. They only depend on the output for these circuits, depend only on what is the input right now. Okay. Now, of course, this has to be taken with a bit of a pinch of salt because all these circuits, being real circuits, take some amount of time to respond. So we are assuming that that response time has been given. But apart from that, whatever is the input now, that is what controls the output. No memory effects in these particular circuits. We will talk about memory effects in circuits soon, but right now let's talk about combinatorial circuits where there are no memory effects. The most common, well, there are many such circuits. One of them, we are going to just touch upon a few very important such circuits. One of them is the Xor Gate or exclusive OR gate, which is so important that it actually has a symbol of its own. Just like OR has a plus, XOR has a plus within a circle. And what is an XOR gate? It's simply the exclusive OR, which is a standard OR in the English language. One standard version of the OR in the English language. So if I said that you have to appear in the exam, in the extra class test that I'm giving, or you will fail. I'm not saying that, but if I did say that, then you have two statements. That is, you are going to appear in the next class test. And the other statement is you will fail. Now, in this case, if I were really serious about it, then the OR here would have to be the exclusive OR, right? You appear in the circuit, in the exam, you don't fail. Then this statement is true. That's fine. You don't appear in the exam, you fail. That's also okay, according to this statement. But if you were to appear in the exam and at the same time you were to fail, that would be rather unfair, right? So 1, 1, which gives you 1 in the usual OR, gives you 0 in the exclusive OR. So exclusive OR is this, is A and not B, or A not and B. That's what the form is. Now there is such an important circuit that it actually has a symbol of its own. So the symbol looks like an OR gate symbol, except that there's an additional curved line at the end, and that's the XOR symbol. And you can easily make it using NOT gates and AND gates and OR gates. That's pretty easy. You can easily see that that's easy to do. Okay. One important reason why the OR gate is XOR gate is so important is that it can be used in a specific manner. Let's say if B is 0, that is, B is either this or this, then whatever A is, A XOR B, you can check that then A XOR B is just whatever A is, right? Of course, if B is 0, then A bar B is of course 0, and B bar is 1, so AB bar is A. So if B is 0, A XOR B is A. And if B is 1, if you look at these two lines, then whatever A is, A XOR B is just the opposite of that, right? Just not that. So A XOR B is A bar. So what you get here is what is called a controlled inverter. It inverts. If one of the inputs is used as a control, then the other input is inverted or not inverted depending on whether this control is low or high. If it's low, it's not inverted. If it's high, the other output is inverted. Okay? Now, this is what we use often in a computer. In fact, this is one of the important parts of a computer. Here what we have is 8 inputs. These are 8 numbers which can take values of zeros and ones, and I hope all of you know that these are called bits, right? We have used the terminology often enough in computers. And so this is basically an 8-bit number which is being given in this form: D7, D6, D5, D4, D3, D2, D1, D0. So 8 inputs which can be either 0 and 1. So you get an 8-bit number form from them. And each of these are being fed to an XOR gate. So there are 8 XOR gates here. And there's something wrong with the circuit diagram. I will tell you what is wrong with this circuit diagram. What is wrong is this. This is the way the circuit diagram should have been drawn. Let me explain that a bit. Okay, I don't really have much space here, so I will just try to make up some space. Let's say, okay, well, this is just a convention, but it's an important convention to be aware of. In an analog circuit, when you draw a circuit diagram, you often see things like this: 2 wires crossing. You see things like this. You also see things like this. In analog circuits, the rule is if you want one wire to cross another without touching. After all, remember, real circuits are there in 3 dimensions. But when you are drawing them on a piece of paper, there may be situations where you may have to make the wires cross, even though they're not joined to each other. And of course, the way you draw them is putting a bump. So if you put a bump like this, it means there's no connection. If you have something like this, it means that there is a connection. So there is a connection here. No connection in this case. This is the convention in analog circuits. Note, that's important. It's in analog circuits that you use this convention. In digital circuits, on the other hand, what you do is you use an entirely different convention. For digital circuits, the standard convention is this is no connection. If you have wires which cross each other, that's no connection. If you want to imply a connection, you have to show the connection. That is, you have to put a blob there that says that these 2 wires are really connected. So although here it was sort of obvious that these were really joined to this line, if you want to use the standard convention, you have to actually show the blobs to show that this wire and this wire are connected. Now, you might ask, why do we use such a convention? The answer is simple. In most digital circuits, you have many wires, and because you have many wires, there are way too many places where the wires cross each other without being connected. So it would be very terrible for people who were drawing circuits if they had to show a jump every time a wire crossed another without a connection. That is why, for digital at least, you have this convention that 2 wires crossing without any shown connection is no connection. In other words, in analog, no connection is actually has to be actually shown. That is, by showing a bump. In digital, connections have to be explicitly shown by putting a blob. So that's a standard convention for drawing, and this is important to remember because otherwise it might confuse different situations. Okay, now let's go back to this. What we were saying is there's a single input, which is of course either 0 or 1. So, and that's being fed to each one of the 8 XORs. So what is going to happen here is, if inv is low, then one input to the XOR gates is low. That means you're going to get the output is going to be the other input. So then Y0, Y1, Y2, etc. is going to be exactly equal to D0, D1, D2, etc. So whatever 8-bit number goes in, the same 8-bit number comes out. But if inv is high, what happens is whatever was there in the input 8-bit number, that gets complemented in the output, which means that if you gave in, say, a number like 10110010, the output is going to be 01, 001101. So can anybody tell me what this operation is called? At least in the context of binary numbers, if you were to take a binary number and change every bit to its opposite, every 1 to a 0, every 0 to a 1, what is that called? Anybody know that?
Bitwise not.
Well, it is bitwise not, of course. That's exactly what you're doing. You're taking every bit and you're applying not to that. You're actually taking every bit and either applying not to that or not doing anything at all, depending on what invis. If invis 0, you're not doing anything at all. If invis 1, you are actually inverting or you're applying the bitwise not. But in the context of binary numbers and not Boolean algebra, there is a special name to this particular operation, changing all the ones and to zeros and all the zeros to ones in a binary number representation. Can anybody tell me what that is? You have not heard of this? You have not heard of ones complement? Haven't you heard of ones complement and twos complement and how to handle negative numbers in a computer? No? That's strange. I hope I did not take your first computer course. Did I? I did take your last semester computer course, but then I assumed that this was already covered. Anyway, ones complement is one way in which negative numbers are often represented. We'll not go into details now. Maybe we'll have to talk about that again soon, but let's just. So if you want to represent a negative, remember in a computer, all you have are zeros and ones. You don't have the luxury of a minus sign or a decimal point, right? So negative numbers are represented by using the ones complement of positive numbers. At least in some cases. There's another way of representing them that we are going to talk about soon. Okay, the next important circuit, something called a half adder. So what does it do? Well, it adds 2 bits. When I say add, I mean really add. Add as in summation, not as in or. Okay, it actually adds. And of course, if you add 2 numbers, well, what are the numbers possibly? 0, 0, 0, 1, 1, 0, and 1, 1. What are the possible sums? For 0, 0, the sum is of course 0. If I write it in using 2 bits, it's still 0, 0. In 0, 1, the sum is of course 0, 1. 1, 0, the sum is 0, 1. 1, 1, the sum is actually 2, but 2 cannot be represented as a single bit. It has to be written as 1, 0 in binary. So this is the binary sum in binary. So that means to be able to sum up 2 bits, the result cannot be written down in a single bit. It has to give it. You have to use 2 bits. One is the carry bit, which is what you get when you add 1 and 1. You cannot fit it into single bit. You have to carry 1 over to the next level. This is of course the same thing that you did long time ago when you added decimal numbers. There of course say 3 and 4 did not give you a carry, but 3 and 8 gave you a carry of 1. So the carry of 1 happens whenever a single bit can no longer hold the sum. And this is the output. This is a sum, which I've written as D here. And now you can easily read off what C and D are, right? C is simply AB, right? A and B. Only when A and B are both high do you get a C, do you get a carry. And what is D? D is 1 whenever either A is high or B is high, but is 0 when both are high. So this is the exclusive OR. So basically, this is the circuit that is going to, since XOR gates are important enough to have their own symbol, I'm simplifying this by drawing just the XOR gate. So this is the half adder. This is basically at the heart, or would have been at the heart of a computer. Because what a computer does essentially is adds numbers really, really fast, and then multiplies, divides, etc., essentially by repeating that algorithm, but doing all this very, very fast. But till I said one thing, I said, would have been at the heart of a computer, but it's not really at the heart of addition. For one very simple reason. If you wanted to add 2 binary numbers, You all know how to add binary numbers, right? I hope. That is, suppose I have a number like 101101 and 010011. So by the way, let's be formal and let's say we are going to use 8 bits to represent a number. Now, of course, modern computer systems usually use 64 bits to represent an integer. That writing down 64 bits will be way too high and will take too long. So I'm just assuming that we are using 8-bit to represent a number. So these 8 bits stand for a binary number, for 2 binary numbers, and you want to add them together. So how do you add them together? Simple. You add them 1 and 1. What do you get? You get? What do you get when you add 1 and 1?
0.
Well, you get 0 as a sum, and you get 1
One on
as
the
a
other
carry.
side.
You actually get 2, right? But 2 is 1, 0. So it's just like when you're adding 73 to 98, 3 and 8 add, give you 11, but 11 can't fit there. So 1 gets down, 1 gets carried. Similarly, 1 and 1 gives you 1, 0. So 0 goes down, 1 goes up here. Next time around, you have to add these 3. So you have 1 and 1 again is 0, 1 carry. 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 1, 0 here gives you 1 and a 0. So that's the sum. Okay. It's just as simple as adding during our childhood. The only thing that you have to note here is that when you want to add 2 binary numbers together, you're not adding 2 bits, right? You're adding 2 bits only here. Everywhere else, you're actually adding 3 bits. The 2 bits which are coming from the 2 numbers that you want to add, and another bit which comes from the carry of the previous step. Okay? Clear? Now that carry could be 0, but even then, when you make a circuit to add up, you cannot have one circuit for when carry is 0, another circuit for when carry is 1. So even if the carry is 0, you have to be able to add it to them. Okay? So the important thing is what you need is not a half adder, and that's why that thing is called a half adder really. What you need is a full adder. And the full adder really has 3 inputs, 2 bits from the input number, the nth bits from the input numbers, and the n-1th carry, the carry from the previous position. These 3 are inputs, and they give you the output sum bit and the nth carry bit. So this is just one full adder. Depending on how many bits your numbers are, you need that many full adders put together to actually add up to binary numbers. So for example, here I've shown a 4-bit addition. So you have two numbers which are written A3, A2, A1, A0. Those are the 4 bits making up the number A. So this is the number A. And the number B has 4 bits, B3, B2, B1, B0. You want to add them together. So what we have done is we have just fed these A3, B3, A2, B2, A1, B1, and A0, B0 to full adders. Okay? 4 full adders. The only thing that I've done is at the very beginning, the first one doesn't have a carry, right? There is no carry from the -1 position. There is no -1 position here. So because there's no carry from the -1 position, you ground this input. Is that clear? So this C-1 is explicitly set to 0. And you just add the other 2. A0, B0 is added. Of course, you're actually adding A0, B0 and C-1. C-1 is just set to 0. So you get an S0 and a C0. But C0 is now fed into the next full adder. A1, B1, C0 adds to give you S1 and C1. The carry goes here and so on. So this is how the thing works out. Okay? So this is how you would add 4-bit numbers. In fact, if your numbers were really 4-bit, then the final carry would be dropped. Okay? Because then you get S0, S1, S2, S3. These are the 4 bits which make up your final answer. Okay? Of course, if these were not 4-bit numbers, but were 8-bit or 64-bit numbers, for 64-bit numbers, you will need 64 full adders, one after the other. Okay? So Of course, what you could have said that is for instead of the first full adder, I could have used a half adder here and used full adders for the rest. But the important thing is you essentially need to add 3 bits. That's why you need a full adder. Half adder will not do for addition. And now, what is the circuit for the full adder? Well, there are 3 inputs, 8 possible combinations. Of course, if all of them are 0, then that sum is 0. 0, 0, 1, the sum is 1, there's no carry, and so on. It's pretty easy to see that if all 3 are 1, then you get 3, right, as an output. So sum is 1, carry is 1. These cases, this one, this, you get, basically in these 3 cases, you get sum of 0, carry of 1. So carry of 1 comes in these 4 cases. So you can try using a kernel map to simplify this circuit, or just use standard Boolean algebra. It's pretty straightforward. The point is, if you look at the carry, it's pretty easy to realize that this carry is something we have already described before. The carry is nothing but the majority thing, right? If 2 or more are 1, the output is 1. That's for the carry. So the carry is simply the majority voting thing. And we have already seen what it's going to be. It's going to be AN, BN. Remember, AN, BN, and CN minus 1 are the inputs. That is, for the third full adder, or full adder number 3, A3, B3, and C2 are the inputs, and so on. So AN, BN, and CN minus 1. Just use kernel maps, or do whatever, whichever way you want it. This is what the CN comes out to be. SN, on the other hand, does not simplify at all. You have 4 ones which are completely disjoint. You cannot make them into boxes or pairs of 2s and so on. So this is what SN really is. Okay. Now the important thing that I want to tell you is this. If you just went by this SN and CN, these are the simplest possibilities, by the way. In fact, the kernel map makes it, not only helps you simplify, it also tells you that when you cannot simplify any further. In this case, because all the ones are detached from each other, there's no way you can make doublets or quadruplets or octets. So no simplification possible. Individual terms, all of them have to be single terms, and that's why you get a big looking expression. Now, if you were to implement this circuit, and you can get a full adder this way. However, and this is where things become a bit more complicated than I led you to believe last time around. I did tell you that the kernel map gives you the way of simplifying this output in the most possible way. You can't do any better than that. That actually is true. However, if there are multiple outputs that you're looking at, in this case for the full adder, you're looking at 2 outputs for every full adder, CN and SN. Then it's possible that you could use part of one output, either the output itself or a part of that output, to simplify the other calculation. Okay. So, because in many situations you would actually want to get multiple outputs, it's very possible that you may have other simplifications beyond what the kernel map tells you. So simplifying such complicated multi-output things is more difficult than just by using a kernel map. And frankly, as long as the number of outputs is small, there are standard techniques which help you do it. If the number of outputs is large, and that's the current scenario, then it's more a matter of art than science. It's some people have the knack of being able to simplify more than other people, and they are the designers very much in demand in the industry. Of course, simplifying a complicated circuit means that you are actually cutting down the cost a lot, so it gives your company a huge competitive edge over a competitor. And which is why developing tools which help simplify complicated situations and the ability to simplify, but which some people have and other people don't seem to have, that becomes a commodity which is in great demand in the industry. But let me just show you what you can do with SN and CN. For that, you just need to do one thing. If you check the complement of Cn bar, well, what is the complement of Cn bar? Complement of Cn bar will look like, if you look at the kernel map for that, Cn bar of course has the same kernel map as this one, except that all the ones are zeros and all the zeros become ones. So now you have a doublet, you have another doublet, and you have another doublet, which is this. Remember, the sides are wrapped around. So you can easily see this is what Cn bar is going to be. Now, that doesn't seem like a big advantage, but if you take this and this with an plus bn plus cn minus 1, that is, of course, an or bn or cn minus 1, and it with Cn bar, then you get this. Okay, just to illustrate why that happens, you can of course break this up into 3 steps: an Cn bar, or bn Cn bar, or Cn minus 1 Cn bar. Since an, bn, and Cn minus 1, each of them have 3 terms, it looks like you're going to get 3 terms for each one of them. That means you're going to end up with 9 terms here, right? Because Cn bar has 3 terms. However, you only get 3. Why? Because if you take this and say you multiply this by an, on the left, on the right, doesn't matter. Multiply, of course, is wrong, but this is something we say all the time. You're ANDing it with an. Whether you're put it on the left or right doesn't matter, because AND is commutative. But if you do this, an times an bar will be 0. An times this an bar will also be 0. So the only term that will survive is an bn bar Cn minus 1. So this term only comes from an. Similarly, from bn, okay, that's not bn bar really, it's just bn. You will get this term. From Cn minus 1, you'll just get this term. Other terms will all cancel out. But this is, of course, almost Sn. Except that Sn, if you look at this, at these 3 terms, it also had an an, bn, cn minus 1, where all the 3 inputs were ANDed. That's the only additional term. So basically, because you're already producing Cn, if you're producing Cn bar, all you need is take Cn bar, AND it with an, bn, cn minus 1, the 3 inputs, and AND the 3 inputs or the whole thing together. That's actually much simpler than creating an Sn bar using this whole combination. That will take a lot more work. So basically, this is how the full adder circuit is built. Basically, what you do is take an, bn, cn minus 1, AND them together to get Cn minus 1, an, bn, cn, an, bn, then OR them to get Cn, but you don't really OR them, you NOR them. That is why you get Cn bar here. Take this Cn bar, combine it with the 3 inputs. You have got Sn as an output. So that's how you make a full adder circuit. The important reason why I wanted to talk about this is that you must realize that the kernel map may not be, or even getting the expressions in the simplest possible form, may not be the final step. Sometimes you have to be clever, and if you have multiple outputs, you may have to use those outputs together. So although I gave you an example of this binary coded decimal, sorry, not binary coded decimal so much, I gave you an example of 7-segment display where we had 8 distinct outputs, 7 distinct outputs for the 7 segments, and we simplified each of the outputs individually. However, it might happen that you may have other further simplifications, but you do have further simplifications. If, for example, you use part of the output which you are using for A, one of the segments, to simplify the connection for B or connection for C, and so on. So that is a rather complicated situation because you have 7 distinct outputs. Finding the simplest possible, that is the one which will take the least number of gates, will be easiest to implement, will be rather difficult. Okay, I will just skip the next topic, but go on to talk about 2 very important circuits. One is called a demultiplexer, the other is called a multiplexer. Let me just magnify this a bit. So these are 2 very important circuits which I'm going to end with. And you will soon see why they are very important. The demultiplexer essentially works this way. If you look at this, on this side, you have 3 lines A, B, marked A, B, and C. These are the 3 inputs. And what I've done is I have one line which is A, another line which is A bar, right? You have put a NOT gate in front. So this blue line next to the red line is A bar. The red line is A, the next blue line is A bar. Similarly, red line is A, the next blue line is A bar. The red line C, sorry, B and B bar. Here this red line is C, the next line, blue line is C bar. I've deliberated, the colors have no other significance. I've just put in the colors simply so that you can see them better. And similarly, the connections that have to be made, I have marked them blue or red. Just to indicate whether they are connected to the A line or the A bar line or B line, B bar line, and so on. So if we look at the connections, forget this D for the time being. If I look at these connections, the 3 blues here, 3 blues essentially mean they're connected to A bar, B bar, C bar. So when is, and this is an AND gate, right? In an AND gate, all inputs have to be high for the output to go high. In an AND gate scenario, suppose you have A, B, C, D in an AND gate. So you're ANDing them all together. And let's say all these are 1. Then the output is simply going to be A. On the other hand, if you have A, B, C, D, and any one of them, not all of them, any one of them is 0, the output is going to be 0. Right? So here we have A, B, C as your control bits in a way. And the 4th bit D is fed to each one of the AND gates. So here you have 8 AND gates connected, marked Y0 through Y7. So the outputs are marked Y0 through Y7. And each of one of them has T as an input. The other 3 inputs, they are different in different cases. In fact, there are 8 possible outputs. Here, you have A bar, B bar, C bar connected to this. Here you have A bar, B bar, C connected. Here is A, B bar, C. So these are the connections. A bar, B bar, C for the top one. A bar, B bar, C for the second one. Then you have A bar, B, C bar for the third one. The next one is A bar, B, C. 1 blue, 2 red. Right? Then you have red, blue, blue. That is A, B bar, C bar, and so on. But if you think in terms of binary numbers, then this becomes very easy. When is A bar, B bar, C bar high? When is A bar, B bar, C bar high? When all 3 are high, right? And that means when, oops. That means when all 3 A, B, C are low. So 0, 0, 0 will give you high value for A bar, B bar, C bar. Then this is 0. All 3 zeros give you 1. Sorry. That is not this one. This one. Yeah. All these 3 inputs will give you 1. So if A, B, C are 0, 0, 0, then all of these are 1. So the output for this is going to be Y0. Y0 is going to be just D. So here Y0 will be D. And all the others you can easily check. Y1, 3, Y7 will be 0. If on the other hand you give say 0, 1, 1, you can easily check that will happen. When that happens, only this particular AND gate, the one whose output is marked by 3, is going to get 0. They're going to get 1, 1, 1 for the 3 inputs, right? Because A is 0, that means A bar is 1. So 1, 1, 1 for the 3 inputs. And D, so the output is going to be D for Y3, 0 for all the rest. So what the demultiplexer really does is that it actually allows you to guide this input D to any one of the 8 lines here. Which one will it go to? It will go, that will be dictated by ABC. So this is how control occurs within a computer. If ABC is set to say 110, that's actually 420, 4 plus 2 plus 0, that's 6 in binary. And 110, Y6 is going to go to D, get D, everything else is going to get 0. So this input D, whether it's 0 or 1, whatever it is, will go through Y6 if you have 110 as your control ABC. So the control bits ABC, there are 8 possible values, and those 8 possible values dictate which one of the outputs get the value D. So you can guide your output to any one of the possible outputs. This amount of control is essential for a computer to learn, to work. Okay, I will just take 5 minutes to explain the next circuit, which is really fascinating and which is very similar to the previous circuit, except if you look at the previous circuit, you had three control lines A, B, C, and A bar, B bar, C bar, and you had connections made. The connections are not haphazard. These are, well, essentially 0, 0, 0. That's why they're connected to A bar, B bar, C bar. This is 0, 0, 1. This is 0, 1, 0. This is 0, 1, 1. 1, 0, 0. So you can realize that this is just 0, 1, 2, 3, 4 in binary, one after the other. The same is happening here, except that instead of having one input D, you have 8 different inputs marked D0 through D7, and they're being fed to these OR gates, and these AND gates, and you are taking an OR, collective OR of all of these and feeding them to the output. So what happens here? What happens is something like this. If ABC, whatever ABC I give, if it's 110, let's say, as I've written, then if you look at this line, the line marked D6, then whatever D6 you have given, that's fine. This is 1, this connection is 1, and this connection, which is going into this AND gate, is actually 1, because C is 0, so C bar is 1. So 1, 1, 1 are the 3 inputs this gate gets, and the last input is D6. So the output to this gate is D6. The output to all the other gates are 0, because one of the ABCs at least is going to give you 0 as an input for that. And now, when you OR them, the output is D6. But can anybody tell me why this is such a fascinating circuit? What's so great about this circuit? This is apparently telling you that if ABC is 110, I get D6. If ABC were, say, 101, what will Y be? Can anybody tell me that? Quickly, we are out of time, so we need to speed this up a bit.
D5.
Yeah, it is going to be D5 because, well, D5 will have 1 from here, 1 from here, because the blue actually is B bar. So since B is 0, you get B bar is 1, and 1 from here. So D5 is the only, this AND gate is the only one which has 3 inputs coming from from the controls as 1. And D5, whatever D5 is, will come out here. All the others will have 0. So the output will be D5. So in this case, you can make the output change to any one of D0, D1, D2, D3 to D7 just by changing ABC. But why is this so useful? Can anybody guess what's so great about this? This is called a...
You can select an input.
No.
Select an input.
Select an input, yes, but it's more than that. This is called an 8x1 multiplexer. 8x1 because there are 8 possible inputs and 1 output, right? The 8 letters in green here are the inputs. These are the controls. Okay. For the 1x8 demultiplexer, you had one input which could be guided to any one of the 8 outputs just by using the control bit. Here, by using the control bits, you can choose any one of the 8 inputs to appear at the output. But can anybody guess what's so great about this? Let's say I have a truth table like this. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1. I can go on. And let's say I have a truth table which gives you 1, 0, 1, 1. And there will be 4. Okay, 4 more. Let me just write down the 4 more. 0, 1, 1. So this is a completely arbitrary truth table. Some function which I just thought up right now. Okay. So now, if I did this, if I took my demultiplexer, let me just memorize this 1, 0, 1, 1. I have lost 0, 1, 1, 0. Okay, You need 8 possible outputs, 8 possible inputs, right? So if I just do this, instead of D0, I put 1. Instead of D1, I put 0. I put 1 here, 0. Okay, sorry. 0 here, 1 here, 0 here. So what will this circuit do? When you give it 0, 0, 0, when you give it 0, 0, 0 for ABC, it's going to give you 1 as output. If you give it 0, 0, 1, it's going to give you D1, which is 0. Here 0, 1, 0, it's going to give you D2, which is 1. So can you see why this is so great? Any ideas? Okay, just let me ask you once again, how many Boolean functions can you have with 3 inputs? Yes? We asked this the last time around as well. You have 3
2 to the
inputs.
power 8.
It's 2 to the 8. Quite a large number, right? 2 to the 8 is how much? In ordinary human language?
256.
256. So there are 256 possible Boolean functions with 3 inputs. Okay, and that means there are 256 different circuits which will implement them, right? But don't you realize that you can do that just by using this one circuit? Any Boolean function you want to implement. Okay. Write down the truth table, write down these in terms of 0, 1, 2, 3, 4, and so on. Just put those values here. And then if you have 0, 0, 0, you're going to get 1 because you're going to get D0. You put in 0, 0, 1, you're going to get D1 because you want the output to be 0 when input is 0, 0, 1, you have made D1 0 and so on. So by using the same circuit, just by changing the input combinations, the D0, D3, D0, D7 combination, you can implement any Boolean circuit with 3 bits that you want. All the 256, one circuit. Okay. Well, why only 3 controls? I've just drawn 3 controls simply because 3 controls is what I could fit within the paper conveniently. Could just use 4 controls, for example. 4 controls means 16 possible inputs, 0 to 15. So I will have 16 possible inputs, D0 to D15, and all the 2 to the 16, which is 64,000 or more different circuits, all of them implemented with one circuit. Okay, that may sound wonderful, and that may also sound like, if that is true, why then are we at all wasting our time talking about Boolean circuits and so on? Why don't we just have one multiplexer and then that does everything for us? You have to realize that the multiplexer is rather complicated, and in most situations, and because the signals have to go through multiple gates, it may become slow. In most situations, it's easier or faster if you use smaller circuits, okay, with less components and cheaper that way. However, this is very important. If you have a complicated Boolean expression and you want to see whether it works correctly or not, very often the fastest way to check that would be to have a multiplexer to which you put in the inputs, you see whether the output works. And of course, you combine it with other circuits and see whether you are getting your desired result. So a multiplexer is very, very important for prototyping. You want to check whether your Boolean algebra is correct or whether you're really getting the output that you want. And you may need to do that for very complicated circuits. Doing everything on a piece of paper may not be good enough. There, people use multiplexers to prototype to check whether the circuits are correct. And once they're sure that the formulae are correct, then they go on and implement them using other smaller components. Okay, so the multiplexer is the final circuit that I'm going to talk about in digital. We have only talked about combinatorial circuits. We have not talked about sequential circuits at all, simply because we don't have time. But we will do that next semester. At least your lab teachers are going to do that. And we have also discussed about certain topics that will be put in the lab. Not put in, that's already there. But what will be emphasized and what will be not will be discussed soon. Okay, so that's it. End of the course. So there should be a collective right now, which of course you must be saying now, but I can't hear because you're all muted, thankfully for me. But anyway, best of luck for the exam. And I will let you know when the last classes will take place. If anybody wants to appear there, you're welcome. You don't have to. That's important. Okay, bye for now.
Thank you, sir.
Okay, thanks a lot. We'll see you again. Unfortunately, you are not getting rid of me that easily. Next semester, you'll see or hear me again. Anyway.